A good example of molecular energy is the following effect called cryophorus. It is just this Pyrex glass construction, two bulbs connected by this tube. An inside bulb is less than half filled with water. Now, if I put this bottom bulb into liquid nitrogen, then the water vapour inside this column condenses out into solid at the bottom and leaves a vacuum above the liquid. And so energetic molecules are going to leave the liquid and be pumped away with this closed pump. The liquid is going to be losing its most energetic molecules, and therefore the liquid is going to cool down. And watch how far we can cool it. You can see the bulb starting to frost up now. It's getting cold enough here that moisture in the air is condensing on it. I'm just shaking it because we have a superfluid in there. Really need to just initiate. Boom, look at that. Just went solid. We've cooled that water down to 0 degrees Celsius where it has turned solid just by pumping away the most energetic molecules and leaving the rest behind. Nice self-contained pump, very simple, and you can see the ice in there. There is no liquid. If I tip this up, nothing runs out. Cryophorus effect, very simple. Right, I should emphasise, this is not just ordinary glass, it is Pyrex glass, one that will withstand a thermal shock, such as putting into liquid nitrogen. Secondly, the amount of water in here have less than half a bulb, because water, when it turns to ice, expands, and we want to make sure that we don't go cracking the glass vessel. In this demonstration, we're going to look at molecular energies. What I have here is a glass thermos flask, actually made out of Pyrex. As this is a demonstration, you're going to be able to show a class. I better put on some safety glasses. So what I'm going to put into here is some liquid nitrogen. Liquid nitrogen is nicely settled. That means the Pyrex containing it is at about the same temperature as the liquid nitrogen, at about minus 200 Celsius. If we now connect up the vacuum pump so that we'll remove molecules from the liquid a lot faster, you can see some vigorous boiling. So we're removing molecules at quite a fast rate. We're taking away the most energetic ones. That means it's the colder ones being left behind. The liquid is cooling, and how cold? Well, look at it now. There's now solid forming. That is solid nitrogen around that top of that liquid. So we've cooled our liquid nitrogen down low enough that it's turned into a solid. It only looks like slushy ice, it's not very impressive at all. But that is air gone solid. It really impresses people when you plunge your hand into molten lead. But actually it's just simple physics. It was a trick used by carnival people 100 years ago and more. How can we do it? Well, first, let's just heat up some lead. Once the lead reaches its melting temperature of 327 Celsius, the temperature will stay constant until all the lead has melted. However, keep heating. For safety's sake, I want the lead to be about 100 degrees above the melting temperature. If the temperature is too near the melting temperature of lead, there is a likelihood that some lead will congeal on my hand, and the last thing I need is an immovable hot lead glove. My hand will get badly burnt. So now it is hot enough. So this is molten lead at 400 degrees, and I'm going to plunge my hand into that. Why can we get away with this? Because of an effect called the Leidenfrost effect. When our moist hand goes into the lead, the liquid immediately turns to vapour, and that shields our hand. Now, why so? We all know that liquids and solids aren't really compressible, so the atoms' molecules are as close as they can get to each other. But equally well, we all know that a gas is very compressible. We see this whenever we use a bicycle pump. If we turn a liquid or a solid into vapour, the volume expansion is about 700 times. Now, I'm a physicist. 700 is close enough to 1,000, and 1,000 is 10 this way and 10 that way and 10 that way. So in a gas, the molecules are about 10 molecular diameters apart. They aren't touching. Gases contain much less heat. They are much better thermal insulator than a liquid or a solid. And that is what protects our hands. There are 3 safety tips for this demonstration. Firstly, make sure you've got short fingernails. You certainly don't want molten lead going up between the fingernail and your finger. You'll get a serious burn. Secondly, make sure that the lead is about 100 degrees hotter than the melting temperature of lead. You don't want a congealing lead around your hand forming a hot glove. You then will get a serious burn. Thirdly, make sure your hand is wet or moist would do to provide the vapour for the protection. I did this demonstration at SciCon 2004. The following day at the workshop on death-defying demonstrations, people were invited to plunge their hand into molten lead. Only one would, and he was a teacher from Papua New Guinea, where it is very hot, so he had a head start amongst the rest. But no one else would actually try it. What a shame.